Hello. Today we want to talk about functions, the ins and outs of making predictions. Functions are one of the most important concepts in mathematics. What is a function? And what makes functions so useful in solving problems and making predictions in the real world? Let's take a look. First of all, let's talk about a mathematical relation. You probably think about the word relation in terms of relationship. If you look on Facebook and you see that a young lady has announced that she is in a relationship with a certain young man, you know exactly what that means. The two are a pair or a couple. Well, a mathematical relation is any set of ordered pairs. If we use the variable x to represent the set of first coordinates of the ordered pairs, and the variable y to represent the set of second coordinates of the ordered pairs, then a function is a special type of relation in which each x is paired with exactly one y. The set of first coordinates, or inputs, is called the domain of the function, and the set of second coordinates, or outputs, is called the range of the function. In other words, each input to a function results in only one output. So if you know what you're putting into a function, you can predict exactly what is going to come out, what will the output be. That's why functions are so incredibly important in mathematics. If real-world phenomena or situations can be modeled by functions, then accurate predictions can be made. The applications for this are so varied. You can use functions to make predictions in business environments. You can use functions to make predictions in the physical world. For example, suppose a bicycle manufacturing company could express its profit as a function of the price that it was going to charge for its bicycles. The company could then try inputting various prices to see which price yielded the greatest profit. The variable that represents the inputs is called the independent variable and corresponds to the horizontal axis on a graph of the function. The variable that represents the outputs is called the dependent variable and corresponds to the vertical axis on a graph of a function. When you think about it, it just makes sense that the output would be dependent on whatever you input to the function. There are four ways to represent a function. We can represent it verbally by a sentence that describes how the input variable is related to the output variable. For example, I could say a function f takes any input and doubles it. If a function has a finite number of ordered pairs, you can specify it numerically just by making a table or a list of those ordered pairs that would match the input values with the output values. Also, you can represent a function graphically by points in a coordinate plane, again remembering that the horizontal axis would represent the input values and the vertical axis would represent the output values. A graph is going to represent a function if and only if it passes what is called the vertical line test. Namely, no vertical line can intersect the graph in more than one point if the graph represents a function. If you think about it, if you have 2 points on a vertical line, they have the same x value or input, but different y values, different outputs. And so if you had 2 points on a vertical line, you would be matching the same input with 2 different outputs, and that would not be a function. A fourth way to represent functions is algebraically by an equation in 2 variables. Let's look at an example to familiarize yourself with function notation. This is read g of x equals x squared plus 2. Remember that the g here is not a variable multiplied by the x. No, g is the name of the function, and this equation is saying that for any input x that you put into the function g, the output will be the input squared plus 2. For example, If I represent G as a machine or like a box here on an assembly line, and I input the number 3 into G, what would be the output? It would be 3 squared plus 2, which is 11. So the function notation would say G of 3 equals 11. That would mean that the point 3, 11 would be on the graph of G. Here's another example. A function h is defined so that h of x is equal to x squared plus 2x. That means h of any input is going to have an output equal to the input squared plus twice the input. This time, instead of inputting a number into h, suppose I input an algebraic expression. Let's say we input x plus 3 into h. What is going to be the output? The input squared plus twice the input. In this case, x plus 3, that quantity squared, plus twice the x plus 3 in parentheses. When you multiply that out and combine like terms, it equals x squared plus 8x plus 15. So we would say h of x plus 3 equals x squared plus 8x plus 15. Which of the following equations represent y as a function of x? The first equation says the absolute value of y minus 2 equals x. The graph of that equation is given here at the top, and you will notice that the point 0, 2 and the point 0, negative 2 are both on the graph of this equation. If x is 0, y could either be 2 or negative 2, because the absolute value of 2 is 2, and 2 minus 2 is 0. The absolute value of negative 2 is also 2, and 2 minus 2 is 0. We have the same input, 0, matched with two different outputs, negative 2 and 2. We have 2 points on the same vertical line. So this equation does not represent y as a function of x. However, look at the second equation, y equals the absolute value of x minus 2. The graph here shows that any vertical line is going to intersect that graph in at most one point. So this does pass the vertical line test. It is a function. Do not be confused by the fact that there is a horizontal line that intersects the graph in 2 points, negative 2, 0, and 2, 0. It's all right to have the same output matched with two different inputs, and you could still have a function that way. You just can't have the same input matched with two different outputs. We said that functions were extremely useful to make predictions. Let's take an example from the physical world. If a ball is thrown directly upward with a velocity of 40 feet per second, its height in feet after t seconds is given by h of t equals 40t minus 16t squared. How might we use that function to make a prediction? What if we ask, how high will the ball be after 2 seconds? To solve that, we would input 2 seconds into the height function h. h of 2 is going to equal 40 times 2 minus 16 times 2 squared. When you work out that arithmetic, it turns out to be 16 feet. So when you input 2 seconds, the predicted output is 16 feet. This means that the ball will be 16 feet high 2 seconds after it's thrown. Let's ask a different question. At what time will the ball hit the ground again? In other words, what input value for t will make the output height h equal to 0 again? To answer that question, we're going to set the height function h of t, which equals 40t minus 16t squared, equal to 0 feet above the ground, and solve for t. I could solve that quadratic equation by factoring. 8t multiplied by 5 minus 2t equals 0. We know that when t is 0, the ground is where the ball has started out. but what would be the time to make the ball hit the ground again? To find that out, I'm going to set the other factor, 5 minus 2t equal to 0, and that yields a result of t equal to 5/2 or 2.5 seconds. So now we know that the ball will hit the ground 2.5 seconds after it is thrown. Hopefully this gives you a little bit of insight into how useful functions can be in making predictions. Throughout the course of your college algebra this semester, you will learn to study many different kinds of functions and so many applications of how those functions can make useful predictions in the real world. There are applications in business, in the physical world, applications applied to health science, and so many others.